Let me take you through the solutions to a grade 11 math final exam. The exam's out of 123 marks. It starts with a section on multiple choice, and then there are short answer questions from all of the units. Functions, rational expressions, transformations, exponential functions, trigonometry, and discrete functions. Let's get started with the multiple choice section. Section 1 of this exam is just 16 multiple choice questions. Let's get started with number 1. For the function f at x equals 3x squared minus 4x plus 1, what is the value of f at negative 1? F at negative 1 is just function notation. That means what's the value of y when x is negative 1? So we'll just replace both of the x's in the original equation with negative 1. F at negative 1 would be equal to 3 times negative 1 squared minus 4 times negative 1 plus 1. And now we'll evaluate that using the correct order of operations. We'll evaluate the exponent first. Negative 1 squared is 1. Then we'll do our multiplications. 3 times 1 is 3. Negative 4 times negative 1 is positive 4. And I see that I just have 3 plus 4 plus 1, which is, of course, 8. So my answer to number 1 is C. My answer tells me that on the graph of the original quadratic, I would somewhere find the point negative 1, 8. Number 2. The range of the function f at x equals negative 5x squared plus 4 is, well, before I look through my possible answers, in order to find the range, which means the set of y values a function can have, I might want to know what the graph of this quadratic function would look like. So let me do a rough sketch of this. I know the simplest quadratic, y equals x squared, just has its vertex at the origin and opens up. But what we have here is a transformed version of x squared. It is negative 5x squared plus 4. If you remember your transformation rules, adding 4 would shift it up 4, so the vertex is now at the point 0, 4. And because the a value is negative, in fact it's negative 5, I know that it is going to be vertically reflected, so it'll now be opening down. Having this rough sketch of this parabola is enough to know what y values this parabola could have. Notice the highest y value it would ever have would be at its vertex, and the y value at the vertex is 4. The y values of any other point on this function are going to be less than 4. So our range, we would have to say y could be any real number given y is less than or equal to 4. So our answer for this one, once again, is C. Number 3, it says, which of the relations is not a function? For a relationship between two variables to be a function, for each value of the independent variable, x, there can only be one value of the dependent variable, y. So each x can only have one y. We use the vertical line test to check that. Just drag a vertical line across each of these relationships. If it touches any of the relationships in more than one spot, then we know it is not a function. Hopefully you noticed when I dragged the vertical line across part B that it touched it in more than one spot. Let me redraw a vertical line through x equals 8 on part B. Notice that vertical line touches the relationship in those two spots. So when x is 8, y could be 2 or negative 2. Two different values of y for the same value of x. Therefore, that one fails the vertical line test and it is not a function. So part B is not a function. Number 4, the curve y equals 3x squared minus 4x plus 8 and the line y equals 3x plus 5 intersect at either no points, 1 point, 2 points, or an infinite number of points. Well, I know when we have a system of equations where one is a parabola and one is a line, there are 3 options for what could happen. The parabola and the line could intersect at 1 point. That's a possibility if the line is tangent to the parabola. The line could intersect the parabola at 2 points if the line is a secant line to the parabola. Or it's possible for the line and the parabola to never intersect. But I could cross off part D. I know D is not right. There's no way there could be an infinite number of points of intersection between a line and a parabola. So how are we going to know if it has no point, 1 point, or 2 points of intersection? Well, we'll set the equations equal to each other. And then we'll start the solving process to see how many solutions for x we can get that would make these two equations equal to each other. Now I notice this is a quadratic equation because the highest exponent on any of the x's is 2. And to solve a quadratic, we always start by setting it to 0. So I'll move all the terms to the left. and I'll collect them at the same time. When I bring the 3x over and collect it with the negative 4x, negative 4x minus 3x is negative 7x. When I bring the 5 over and collect it with the 8, 8 minus 5 is positive 3. Now that the quadratic is set to 0, one method for solving a quadratic is using the quadratic formula. But we're not actually interested in what the solutions are. We just want to know how many solutions does it have. So in quadratic formula, which I'll remind you of, the discriminant, which is the part underneath the square root, the b squared minus 4ac, can tell you how many solutions the quadratic will have. If b squared minus 4ac is less than 0, there would be no solutions. So that would correspond to the answer for part A. If we get a b squared minus 4ac that is less than 0, I'll know there are no points of intersection because there would be no solutions to the system. If b squared minus 4ac was equal to 0, that would mean that there is one solution, and therefore one point of intersection between the line and the parabola. If b squared minus 4ac was greater than 0, I know I would get two solutions to this quadratic equation, meaning there would be 2 points of intersection. So let's check what b squared minus 4ac is for this quadratic. I'll label the a, b, and c from this standard form quadratic, and now I'll evaluate what is b squared minus 4ac. It would be negative 7 squared minus 4 times 3 times 3. If I evaluate this, I would have 49 minus 36, which is 13. That's a number that's greater than 0. That tells me that there would be two solutions to this quadratic. I don't care what the solutions are, I just know there would be two of them, which means the line and the parabola would intersect at 2 points. So the answer to this one is C. Number 5, for the function f at x equals 2x squared minus 5x plus 1, if f at a equals 4, what's the value of a? This is just basically asking at what x value will the y value be 4. So I'll set the y value of the function equal to 4, and I'll solve for the x value that makes this true, but it is called the x value, it's called it the parameter a. So I'll replace each of the x's with a, and now I'll try and solve for what value of a makes this true. Once again, this is a quadratic that needs to be solved, so I will set it to 0 by moving the 4 to the other side and collecting it with the 1. And now I need to solve this quadratic. Quadratic formula would work, but I notice that this quadratic is factorable, so maybe I'll solve this by factoring. Because the a value is not 1, it's 2, I need to find numbers that have a product of a times c. So a product of 2 times negative 3, which is negative 6, and a sum of b, which is negative 5. The numbers that work would be negative 6 and 1. What do we do with those two numbers? We split the middle term into negative 6a plus 1a, and then leave the rest of the equation the same. I then factor by grouping. By taking a common factor from the first two terms, I could take out a 2a, divide them both by 2a to get a minus 3. From the last two terms, all I could take out is a 1, and when I divide them both by 1, I get a minus 3 again. I'll continue over here. Notice that I have a common binomial of a minus 3. When I remove that as a common factor, all I'm left with is 2a plus 1. Now using the zero product rule, I know a product of two factors is 0 if either of those two factors are 0. So I'll set both of the factors to 0 and solve each of those equations. I get an a value of 3 and an a value of negative a half. Now I don't see negative a half in the list of possible answers, but I do see 3, so I know my answer to this is B. Number 6 says find the restrictions on this rational expression, 2x squared plus 5x plus 3 over 4x squared minus 9. Restrictions are values that make the function undefined, and that happens when the denominator is 0. So let's just figure out how can this denominator, 4x squared minus 9, how can that be equal to 0? Whatever value of x makes that be 0. That's what would make the denominator be 0, which would make the fraction be undefined. So to solve this one, this quadratic is easy to solve because it's just two terms. We can just move the 9 to the other side. Then we can divide the 4. And then we can move the squared. Whenever we're algebraically rearranging, we're always doing the inverse operation. So the inverse or opposite of squaring is plus or minus square rooting. So x would equal plus or minus the square root of 9 over 4. And 9 and 4 are both perfect square numbers, so let's go ahead and square root them. The square root of 9 is 3, the square root of 4 is 2. So I get plus or minus 3 over 2 as the values of x, which make the denominator 0, which are the restrictions of the function. So my answer for this is part C. Number 7. When the graph of g at x equals 3 times f of 2x minus 2 minus 1 is graphed based on f at x, what is the horizontal translation? Well, remember, a transformed g at x function based on f at x can have 4 transformations done to it. It can have an a parameter, a k parameter, a d parameter, and a c parameter. The horizontal translation is based on the d parameter. But also an important thing to notice here is that k is always factored out from x minus d, but in our question, it hasn't been factored out yet. So let me go ahead and factor it out. The coefficient of the x is 2, so let's factor that out. And then I'll divide both the 2x and the 2 by the 2 I factored out to get me x minus 1. So now you should see that the d parameter is 1, which means we're actually moving 1 unit to the right. C. A coterminal angle for 240 degrees is, and there are 3 options, 60, negative 120, positive 120, or part D, which says 2 of the above answers are correct. Well, what is a coterminal angle? A coterminal angle is an angle that has the exact same terminal arm. So let me draw a graph. Remember, when graphing a terminal arm, a positive angle starts at the positive x-axis and moves counterclockwise. So I know 240 degrees would land me about right here. Now I want to check, do any of these 3 angles have the exact same terminal arm as 240 degrees? Would they land me in that exact same spot? Well, let me draw 60. I'll do that one in red. 60 would land me here. That's definitely not in the same spot. That is not coterminal with 240. Let me now try negative 120. A negative angle means from the positive x-axis, move clockwise. If I move clockwise 120, well, I would go 90 and then 30 more. That would land me, hey, right in the exact same spot. So 240 and negative 120 are coterminal angles. Now the question says, well, maybe 2 of them are correct. So let's also draw 120 and see where that lands. 120 is a positive angle, so I'm going counterclockwise from the positive x-axis. 120 would be roughly right here. That terminal arm is not in the same spot, so it's not coterminal with 240. The only one that was coterminal with 240 was negative 120. B. Now there's another way we could have done this question. I know that the difference between coterminal angles is 360 degrees. If I'm at 240 degrees and I want to find a coterminal angle, I can just subtract 360 or add 360 and end up in the exact same spot. So I could have just taken my 240 degrees and then added or subtracted 360 to find a coterminal angle. If I'd have done that, subtracting 360 from 240, I would have got my answer of negative 120. So I would have known that they are coterminal. 9. The related acute angle, which we call the reference angle for 210 degrees is, let me start by drawing the graph again. Well, 210 degrees, if I start at positive x and go counterclockwise 210, I would pass 180 degrees. It would take me to about right here. The reference angle is always the angle between the terminal arm, so that blue angle I just drew, and the closest x-axis. So the angle between 180 and 210 is 30 degrees. We can find that just by finding the difference in those two numbers, and that's the related acute angle. So my answer is A. 10. The graph of the cosine function is the same as the graph of a sine function that has been translated, and there's a bunch of options. Let me just quickly graph sine and cosine so you can see what translation we would have to do to sine to make it equal to cosine. All right, so I roughly sketched sine and cos. If you wanted to, you could have made tables of values for both to figure out the ratios at each of those angles to graph it, but hopefully you know those basic graphs. What you should notice is that if we took this sine function and moved it 90 degrees to the left, it would line up exactly with the cosine function. So I could say that a cosine function is the same as a sine function that has been translated 90 degrees to the left. B. Number 11, the maximum value of y equals sine x minus 6 is, well, remember this is a transformed sine function. Let me just quickly remind you what the parameters are that could transform sine. It could have an a being multiplied in front. It could have a k and a d transforming it inside brackets and a c outside the brackets. We can find the max value of a transformed sine or cos function by taking your c value, which is the vertical shift, so it's going to shift the midline of the function, and then adding the amplitude, which is the absolute value of a. That's the distance from the midline to the max. So if we go to the midline and add the amplitude, that'll give us the max. In this question, the c value is -6, and the a value, which I don't see 1, so I know it's a 1 there, the absolute value of 1 is just 1. So -6 plus 1 is -5. That must be the maximum value. The answer is B. 12. Determine how many x-intercepts the function y equals 3 cos x plus 5 has between 0 and 360. I like this question. There's a couple different ways we could do it. Your first instinct might be to try and solve this algebraically, and that would be fine. I know at an x-intercept, y is 0, so I could set y to 0, and then try and solve this equation for x. I'd isolate cos x by subtracting the 5 over and then dividing the 3. And then if we're trying to find an angle that has a given ratio, you would probably ask your calculator what is inverse cos of -5 over 3. Now, before you even type this in, hopefully you know there's not going to be an answer to this. Remember, a cosine ratio has to always be between -1 and 1. It can't be less than -1 or bigger than 1. So this value of -1.67 is not a possible cosine ratio we could have. So there's going to be no solutions to this. If you did take the time to type it on your calculator, it'll just say error. Another reason you should know that this has no solutions, well, if you made a rough sketch of what this would look like, this is just a transformed cos function that has an a value of 3 and a c value of 5. Remember, the maximum value is c plus the absolute value of a, so 5 plus 3 is 8. So the highest it would go is 8, and the lowest would be c minus the amplitude, so 5 minus 3 is 2. The lowest it would go is 2. So this function is always going to be going up and down between 8 and 2. It's never going to go below 2. So how many times does this function cross the x-axis? It doesn't. Let's move on to 13. We're now on to some discrete functions questions. Given the general term, Tn equals 3 times n plus 5, which is the first 4 terms of the sequence? Well, I know in a formula for the general term, Tn means the value of the term, and n just means the term number. So if I want the value of term 1, I would do 3 times 1 plus 5, which is 8. If I wanted the value of term 2, I would do 3 times 2 plus 5, which is 11. And you could keep going to find term 3 and term 4, just to verify that in fact C is the correct answer, but notice that's the only one that starts with 8 and 11, so we know our answer is C. 14 says, which sequence is geometric? A sequence is geometric is if there is a common ratio between consecutive terms. Or another way of thinking about that, to get from one number to the next in the sequence, we would multiply by a number. Well, if I look at part A, if I look at the first 2 numbers, the ratio between those two, do the second number divided by the first number, 2 divided by 1 is 2. But then if I find the ratio in the second pair of numbers, 2 and 3, 3 divided by 2 is 1.5, so it's not a common ratio. Part B, the ratio of the first 2, 4 divided by 2 is 2, but the ratio of the next pair, 6 divided by 4, is 1.5. So not a common ratio there either. But part C, 4 divided by 2 is 2, 8 divided by 4 is 2, 16 divided by 8 is 2. There is a common ratio. Or like I said, you can imagine multiplying by 2 each time to get from one number to the next number. So that means C is our geometric sequence. 15, which is the correct expression for the amount a $1,000 investment is worth after 3 years if interest is paid at 4%, compounded semi-annually. Our formula for compound interest, the amount, is equal to our principal amount times 1 plus the interest rate that we're given, divided by the number of times that interest is given in a year, all to the exponent of the number of times the interest is given in a year times the number of years. If I plug in what I know into this question, the principal amount was $1,000. The interest rate was 4%, so annually they're getting 4% interest. I'll write that as a decimal, 0.04. But because they're compounding it semi-annually, they're going to get interest paid twice a year. So instead of getting 4% once a year, they'll get half of that 2 times a year over 3 years. If we simplify this a little bit, I have 1,000 times 1 plus half of 0.04, so that's 1.02 to the power of 6. And I see that right here, part B. A colony of ants has an initial population of 200 and doubles every day. A function that can be used to model the ant population P after t days is, well, an exponential function is always of the format a times b to the x, where a is the initial value, b is the growth or decay factor, and x is the number of times that it's going to be multiplied by the growth or decay factor. So when we make the equation for what this question gives us, it says instead of using y, use p for population, and we'll write it in function notation because our independent variable is t, days, equals a, which is our initial amount. The question tells us that's 200. And the growth factor is what it's repeatedly being multiplied by, which is 2, because it's repeatedly doubling every day. And we want to use t for the number of days. So our function is 200 times 2 to the t. A. That's the multiple choice section done. Let's move on to the short answer section. Section 2 of the exam is on the unit where you were introduced to functions. This is out of 24 marks. Question 17 says, using the graph of the relationship f at x shown to the right, part A, state the domain and range of the relationship. Well, remember the domain is the set of x values the function can take, so where horizontally does this function exist? I want you to notice that the function has an arrow indicating it goes forever to the left, but the furthest right the function goes would be this point right here, which is the point -3, 2. The x value of that point is -3. That is the biggest x value this function could have. All of the x values of all of the other points that make up this function are going to be less than -3. So we'll say the domain of this function, x can be any real number, given x is less than or equal to -3. When we're trying to state the range, we're looking at what's the set of y values that the function can have. Or another way of saying that would be where vertically does this function exist. Notice the arrow indicates that the function is going to continually get higher, so it's going to go infinitely high. But the lowest the function ever goes is that same point I have labeled on the right side of it, that point -3, 2. Since we're doing range, we're looking at the y value of that point. The y value is 2. All of the other points that make up this function will have a y value that's bigger than 2. So for the range, y could be any real number, given the y value is bigger than or equal to 2. Part B says, is the relationship a function? And then justify our answer. If it's a function, for each value of x, there should only be one value of y. And a way to check that is using the vertical line test. If we drag a vertical line across this function, notice it only ever touches the function in one spot at a time, so it passes the vertical line test. This is a function. So I'll say this is a function because for each value of x, there is only one value of y. We could also add a note that it passes the vertical line test, but I think that's enough to answer the question. Part C says, what is the value of f at negative 7? That just means when x is negative 7, what is the y value of the function? Let's go back up and look. Just going to erase the other points we have. When x is negative 7, the function is up here at a y value of 4. I can see from that point that I've labeled that when x is negative 7, y is 4. So my answer to part C, f at negative 7, is equal to 4. 18. Solve the following quadratic equations using the most appropriate method. Solve by factoring where possible. Give simplified exact answers only. Part A, I see that the quadratic is set equal to 2, and I know before I start solving it, I'll have to set it to 0. So let's move the 2 to the other side. 0 equals 2x squared minus 10x plus 14 minus the 2 I bring over will be positive 12. Now, whenever you're solving a quadratic, we should always check for a common factor first. I noticed that all three terms are even, so I could common factor out a 2. And then to get my second factor, I need to divide all three terms by the 2 I took out, which gives me x squared minus 5x plus 6. The quadratic inside the brackets is a trinomial, so I could try and factor it using the sum and product method. I would try and find numbers who have a product of just the c value. Since the leading coefficient is 1, I just want a product of 6. And a sum of the b value, which is the middle term, negative 5. The numbers that satisfy this product and sum are negative 2 and negative 3. They multiply to 6 and add to negative 5. Because the leading coefficient of that quadratic in the brackets is 1, I can go right to my factors, where in each of the factors they both start with x. And then to those x's, I just add the two numbers that satisfy the product and sum. So I'll add the negative 2 and add the negative 3, which gives me the factors of x minus 2 and x minus 3. Now I can use the zero product rule to finish solving this equation. I know a product of factors is 0 if any of the factors are 0. So let's look, how could I make any of these three factors be 0? Well, the constant factor 2, that can't be 0, it's always 2. But x minus 2 could be 0 if x was 2, so there's my first answer. And x minus 3 could be 0 if x was 3. There's my second answer. So there are two answers to this quadratic. You should take your time on an exam to take both of those answers you found, sub them back into the original equation, and make sure the left side is equal to the right side, and then that verifies you have the correct answers. Part B. The leading coefficient is not 1, it's a 3, and it can't be common factored out. So if I were to try and do sum and product factoring, I would be looking for numbers that have a product of a times c, 3 times 5 is 15, and a sum of the b value, which is negative 10. There are no two numbers that multiply to 15 and add to negative 10. So this quadratic is not factorable. When a quadratic is not factorable, you try quadratic formula to see if it can find you solutions. When a quadratic is not factorable, that means there are no rational solutions, but quadratic formula might be able to find us some irrational solutions. So we'll try it. Quadratic formula is x equals negative b, so in this case negative 10, which is 10, plus or minus the square root of b squared, so negative 10 squared, minus 4 times the a value, which is 3, times the c value, which is 5. And that all needs to be divided by 2 times the a value of 3. We'll simplify underneath the square root. That's actually going to tell us a lot about how many answers we'll have to this quadratic. When I simplify underneath the square root, I get 100 minus 60. That's 40. So I have 10 plus or minus root 40 over 6. The discriminant, the number underneath the square root, is bigger than 0. So that tells me there are going to be two solutions to this quadratic. And I also noticed that 40 is not a perfect square number. So it can't be square rooted to get an integer, which tells me we're going to get irrational answers here. And that just verifies that, in fact, we were not able to solve this by factoring. So we're doing the correct method here. We just have to go ahead and simplify that radical expression. There is a perfect square number that goes into 40. 4 goes into 40. So I could split that expression into root 4 times root 10. But the square root of 4, I know what that is. The square root of 4 is 2, so I'll replace root 4 with 2. And then in the numerator, I have two terms. I have a 10, and I have a 2 root 10. I notice both of those terms are even, so I could common factor a 2 from both. When I divide the 10 by the 2 I took out, I get 5. And when I divide 2 root 10 by the 2 I took out, that's just root 10. And that's all over 6. Why did I take out that 2? Because notice I have a factor of 2 being divided by 6. I could reduce that. 2 goes into 2 one time and into 6 3 times, so it reduces to 1 over 3. Let me write my final answer here. I would say x equals 5 plus or minus root 10 over 3. That can't be simplified any further. And the question said it wants exact answers, so we will not type that in to get the approximate answers. Let's move on to question 19, which says, fully simplify each expression, show your work so it is evident you simplified and not just input on your calculator. When we simplify any of the radical expressions in these questions, we check what's the biggest perfect square number that divides evenly into any of the numbers underneath the square root. In part A, I see 150 under a square root, and I know that the biggest perfect square number that divides evenly into 150 is 25. So I could split 150 into root 25 multiplied by, well, how many times does 25 go into 150? It goes into it 6 times. So I can split it into root 25 times root 6, because 6 times 25 is 150. Why did I split into those two factors? It's because I can take the square root of 25. The square root of 25 is 5. So root 150 simplifies to 5 root 6. You could, for this question, also just use your calculator to check and make sure these two values have the same approximate value. Type the square root of 50, see what its approximate value is. Type 5 root 6, check what its approximate value is, and they should have the exact same approximate value. And that's a way for you to know that you have simplified properly. In part B, we have two radical expressions that are being multiplied together. In that situation, you multiply the coefficients of the radicals together. 2 times 5 is 10. And then you multiply the radical expressions together. Root 10 times root 2, we could simplify that by doing the square root of what 10 times 2 is, which is 20. So I have 10 root 20. But then anytime we have a radical expression, we check, are there any perfect square numbers that go into the number under the square root? 4 goes into 25 times, so I could split root 20 into root 4 times root 5. Why did I bother doing that? Well, because the square root of 4 is 2. So I can square root 4 to get 2. And then you can always multiply two constant factors together. 10 times 2 is 20. So my final simplified answer would be 20 root 5. Part C, we have some radical expressions being added and subtracted together. Before I look for like radicals to collect, and there aren't any yet, I want to simplify any of the radical expressions I see. The square root of 48, the biggest perfect square number that goes into 48 is 16, and it goes in 3 times. So I can split root 48 into root 16 times root 3. Minus 5 times root 27, the biggest perfect square number that goes into 27 is 9, and it goes in 3 times. So I'll split it into root 9 times root 3. The 2 root 3 can just stay the same. Nothing to simplify there. But the root 32, 16 is a perfect square number that goes into 32, and it goes in 2 times. So I'll split it into root 16 times root 2. Now all of the perfect square numbers that I have split these radicals into, I can actually square root all of them. The square root of 16 is 4. The square root of 9 is 3. And the square root of 16 is 4. Let me put any constant factors together. 3 times 4 is 12, so I have 12 root 3 minus 5 times 3 is 15 root 3 plus 2 root 3 minus 4 root 2. Notice 3 of my terms are what we call like radicals. They have the exact same radical part of their expressions. They're all root 3s. So I can collect them together by keeping the root 3 and just adding or subtracting the coefficients. 12 minus 15 is negative 3. Plus 2 is negative 1. So I just have a negative 1 root 3, which I can just write as negative root 3, minus 4 root 2. Those cannot be collected together because the numbers underneath the square root are different numbers, so they could not be collected. They are not like terms. That's my final answer. Question 20 says, determine the vertex of the quadratic function, f at x equals negative 5x squared plus 30x minus 37, by completing the square. Verify your answer using partial factoring, then state if the vertex is a max or min point. Completing the square is a process of getting a standard form quadratic into vertex form. The process for doing that is to put the first two terms in brackets, leave the constant value outside of the bracket. If there's a coefficient in front of the x squared, you must common factor it from those first two terms that you grouped. When I divide the first two terms by -5, I get x squared minus 6x. Then inside the brackets, we want to add and subtract a number that's going to make the quadratic inside be a perfect square trinomial. How we do that is we take the coefficient of the second term in brackets, we cut it in half, and then square it. Half of 6 is 3. When we square it, we get 9. So I'll put 9 in both of those spots. We don't want the -9 in the brackets, so we'll get it out of the brackets by multiplying it by the number in front. So outside of the brackets, -5 times -9 is positive 45. All we have left to do is factor that quadratic that is inside the brackets. What numbers have a product of 9 and a sum of -6? The numbers that work are -3 and -3. So that quadratic in brackets would factor to x minus 3 times another x minus 3, which I could just write as x minus 3 squared. And outside of the brackets, 45 minus 37 is positive 8. That quadratic is in vertex form. The vertex is equal to hk, where h is what we're subtracting from x in the brackets, so 3, and k is what we're adding outside of the brackets after the squaring, so 8. That means our vertex is at 3, 8. Is it a max or a min? Well, because the a value, -5, is negative, that tells me the quadratic opens down, which means the vertex is at the top. It's a max value. Let's verify this answer using partial factoring. Partial factoring is another method for finding the vertex. Partial factoring, what you do is you set the quadratic equal to the y-intercept. Remember, the constant term is the y-intercept. So I'll set the quadratic equal to -37. And now what I'm going to do is solve this equation. Let me just show you graphically what partial factoring is about before I do it. What do we know about this quadratic so far? We know it has a y-intercept of -37. And we know it opens down. And we think the vertex is at 3, 8. We're going to verify that during this question. Because parabolas are symmetrical, I know there's another point on this parabola somewhere that has a y value of -37 as well. If I can find where that other point is, I know the vertex is going to be right in the middle of those 2 points. I can just average 0 and the other x value to figure out the x-coordinate of the vertex, and then use that x-coordinate of the vertex to find the y-coordinate of the vertex. So by solving this equation that I've made, I should get 0 and something else. Let's solve it and find out. We'll move the -37 over. Notice when we move that -37 to the other side, it cancels out with the -37 on the other side. So all you're left with is a 2-term quadratic, which you can try and solve by common factoring. I'll divide both the terms by -5x, and that gives me x minus 6. I have 2 factors being multiplied together that equal 0. Using the zero product rule, I can just set each factor to 0 and solve how each of those factors could be 0, and then those are solutions to my equation. Divide the -5 over to give me 0. Add the 6 over, which gives me 6. I have 2 solutions for x. So I've figured out that the x coordinates to have a y coordinate of -37 are 0 and 6. Where is the vertex in relation to those points? I know it's going to be right in the middle. So I can find the x coordinate of the vertex just by adding those 2 x values together and dividing by 2, finding the average of them, which is 3. And I can find the y coordinate of the vertex just by taking 3 and subbing it into the original equation. If I evaluate this using the correct order of operations, 3 squared is 9, multiplied by -5 is -45, plus 90 is 45, minus 37 is 8. So I have just verified that my vertex is at 3, 8. So we have the correct answer. 21 says, for what value of k will this line, y equals -2x plus k, be tangent to the parabola 3x squared plus 4x minus 1? If the line is tangent to the parabola, it means it just intersects it at one single point. So the system would look something like that. How can I tell if the two equations are only equal at one point? Well, we'll start by setting the equations equal to each other. And notice this is a quadratic, so we'll set it to 0, move every term to the right. Notice I've put the k beside the constant because k is a constant. We're just trying to solve for that value of k. That would make this quadratic only have one answer. Let me just collect the middle two terms. The 4x plus 2x is 6x. And notice this quadratic is in standard form, where 3 is the a value, 6 is the b value, and whatever -1 minus k is, that's our constant value, which we call c. We want this quadratic to have one solution so that the line is tangent to the parabola. And I know from quadratic formula, the discriminant, b squared minus 4ac, equals 0 when there's one solution to a quadratic. So we will actually set b squared minus 4ac equal to 0, which in this case would be 6 squared minus 4 times the a value of 3 times the c value of -1 minus k. And we just have to solve this for k. 36 minus 12 times -1 minus k. We'll distribute that -12 into the brackets. -12 times -1 is positive 12, and -12 times -k is positive 12k. We have 48 equals -12k. Divide the -12 over, and my final answer would be 48 over -12, which is -4. If this k value of the line was -4, that would make the linear quadratic system only have one solution, which means the line would be tangent to the parabola. The next section of the exam, we just have to simplify a couple rational expressions. 22 says fully simplify and state the restrictions of the following expressions. We'll simplify the expressions first, and then I'll talk to you about what the restrictions would be. Part A, I have two fractions being subtracted. I know in subtracting fractions we need a common denominator, but before I worry about that, we should always look and see, is there anything that can be factored in any of the expressions in any of the numerators or denominators of the fractions? I notice that the denominator of both of the fractions can be simplified. X squared minus 5x plus 6 is a quadratic with a leading coefficient of 1, so I just find numbers that multiply to 6 and add to -5. Those numbers are -2 and -3, so it factors to x minus 2 times x minus 3, minus 4x over the quadratic in the denominator once again has a leading coefficient of 1. So I just find numbers that multiply to c, -12, and add to b, 1. The numbers that work are 4 and -3. Notice both of the denominators have a factor of x minus 3 already. The fraction on the right has a factor of x plus 4 as well that the factor on the left doesn't have. So I'll need to multiply the left fraction by x plus 4, top and bottom. And the fraction on the right is missing the factor of x minus 2 that the left fraction has. So I'll multiply it by x minus 2, top and bottom. Notice that if you look at the two denominators, they have the exact same set of 3 factors. So I can now rewrite this as a single fraction. Be careful not to cancel any factors at this step because the numerator is not in fully factored form. We would have to expand it completely first and then check if it can refactor before canceling anything. When I expand the numerator, I'll distribute the 9x into the binomial and distribute the -4x into the binomial. I would get 9x squared plus 36x minus 4x squared plus 8x, all over the common denominator. When I collect my like terms, I would have 5x squared plus 44x. In the numerator, I suppose I could common factor an x from both terms, but that's not going to help me cancel any factors, so we could leave the numerator the way it is. Our simplified expression is exactly what I wrote above. And then we also have to state the restrictions. And that means, are there any values of x that make the expression undefined? An expression is undefined if the denominator is 0. The restrictions are on the original function. We haven't canceled anything out at any point, so our final answer, we can find the restrictions from that as well. In the final answer, notice that The denominator is in factored form, so it'll be easy to see what would make the denominator be 0. The denominator would be 0 if any of those three factors would be 0. The first factor would be 0 if x was negative 4. The second factor would be 0 if x was 2. And the third factor would be 0 if x was 3. When we state the restrictions, we say x cannot equal any of those numbers, negative 4, 2, or 3. Part B, I have two fractions being divided. When multiplying or dividing fractions, we do not need a common denominator, so I don't have to worry about that. But I still should factor any expressions that are factorable before trying to do any of the actual operations between the fractions. I see there's 3 quadratics here which have leading coefficients that are not 1 and can't be factored out. So I'm going to have to factor all 3 of these by decomposition. I'm going to do that quickly for each of them, and then I'll erase my work as I go. So for the top of the first fraction, I will be finding numbers that have a product of a times c, 6 times negative 35 is negative 210, and a sum of the b value negative 11. The numbers that work, I think it would be negative 21 and 10. So I split the middle term into negative 21x plus 10x. I'll take a common factor from the first 2 terms. I could take out a 3x, which leaves me with 2x minus 7. And the last 2 terms, I could take out a 5, which leaves me with that common binomial of 2x minus 7. Factor out that 2x minus 7, and I have 3x plus 5 as my second factor. So all of that work just to know that I could factor the top of the first fraction to 2x minus 7 times 3x plus 5. Now I'm going to use that same process for the bottom of the left fraction. I'm not going to explain it this time. You can just watch me do it, and I'll fast forward it so it goes by quickly. Now I have to do the top of the right fraction. In the bottom of the right fraction, the leading coefficient is 1, so that's a lot easier to factor. We just find numbers that multiply to the c value negative 15 and add to the b value of negative 2. The numbers that work are negative 5 and 3. So I go right to my factors of x minus 5, x plus 3. Now when you're dividing fractions, hopefully you remember the rule that at this point in the process, don't try and cancel anything. We want to change this to a multiplication question by keeping the first fraction the same, changing dividing to multiplication, and flipping the second fraction. If you have the same factor in the numerator and denominator of its own fraction, then you can always cancel those out, no problem. But when fractions are being multiplied together, you can also cross-reduce. You can multiply a factor that's in the numerator of one fraction with the denominator of the other. And notice I can also cancel this x plus 3 with that x plus 3. And then all that's left is an x minus 5 over an x minus 1. The first fraction, everything canceled out, so that just equals 1. So we have 1 times the second fraction, which is just x minus 5 over x minus 1. So our final answer for this is x minus 5 over x minus 1. We also have to state the restrictions. And remember, these restrictions are on the original expression, but it's best to look at your format where it has been factored. In the factored form, so the first line of my answer, I would look, how could this expression be undefined at all? Well, I know either fraction would be undefined if either of the denominators were 0. The denominator of the first fraction would be 0 if x was 7 over 2 or negative 3. So I'll say x cannot be 7 over 2 or negative 3. The denominator of the second fraction would be 0 if x was 5 or negative 3. I don't have to write negative 3 again. I already have it listed. There's actually a couple more restrictions here. Notice when this is a division question, if that whole second fraction had a value of 0, then we wouldn't be able to do the division because we can't divide by 0. And what would make the second fraction be 0 is if its numerator was 0. So we also have to check the numerator of this one. X can't be negative 5 over 3 or 1. Section 4 is on transformations. Question 23 says, given the graph of f at x, determine the equation of the inverse of f at x and graph it. Also state if the inverse is a function or not. Well, I'm going to start by, in the equation for f of x, I'm going to change that function notation f of x. I'm going to change it to just y equals. And if I want to find the equation of the inverse of this function, I know inverse functions have their x's and y's switched. Or another way of thinking about it, inverse functions are opposites of each other. So I need to apply all of the opposite operations to x. And how I can do that is by swapping x and y with each other in the equation, and then use algebra to isolate y using inverse operations. I'll start by subtracting the 5 to the other side and dividing the negative 1. Since both of the terms on the left are being divided by negative 1, I can just change the sign of both of the terms. Make it negative x plus 5. Now I need to move the squared to the other side. The opposite of squaring is square rooting, and don't forget, when we do the inverse of squaring, we have to do plus or minus of the square root. And the last step would just be to add the 1 to the other side. I'll put it in front of the radical expression, and that's the equation of the inverse of f of x. So I should use the proper notation. I'm going to replace y with the symbol for the inverse of f of x. So there's the equation. The question also asked me to graph the inverse of f of x. I actually don't need the equation of it to graph it. Since I have the graph of f of x, I can just look at a bunch of points that are on that graph. Let me plot a few and label them. So I've labeled a bunch of points that are on this function. Inverse functions have their x's and y's switched. So for each of these points, I'm just going to swap their x and y, and then plot that point on the inverse function. If on the original function there's the point negative 2, negative 4, I know on the inverse there'll be the point negative 4, negative 2. F of x has the point negative 1, 1, so the inverse of f of x will have the point 1, negative 1. Instead of 0, 4, it'll be 4, 0. And instead of 1, 5, it'll be 5, 1. Instead of 2, 4, it'll be 4, 2. Instead of 3, 1, it'll be 1, 3. And instead of 4, negative 4, it'll be negative 4, 4. If I connect those points, that is roughly the graph of the inverse of f of x. I just had to switch all the x's and y's of the points of the f of x function. And let's not forget the last part of this question where it asks if the inverse of f of x is a function or not. Notice it fails the vertical line test. For lots of values of x, there's multiple values of y. So this is not a function. Let's move on to question 24. The base function, root x, is transformed by a vertical reflection across the x-axis, followed by a vertical stretch by a factor of 2, horizontal compression by a factor of 3rd, horizontal translation 2 to the left, and then 1 down. Determine the equation of the transformed function, g of x. Well, I know g of x is a transformed root x function. Let me just remind you where the parameters a, k, d, and c would go. G at x would equal, the a parameter would be in front of the square root function, k and d would be inside of the square root function, and c would be off at the end. So from the question, let's pull out what a, k, d, and c are, and then let's write the transformed equation. A vertical reflection across the x-axis tells me my a value is negative, and the fact that it's also a vertical stretch by a factor of 2 means my a value is negative 2. K, a horizontal compression by a factor of 1/3. Well, I know the horizontal stretch or compression that's done is based on the reciprocal of the k value, so the k value must have been 3. To move 2 units to the left, the d value must be negative 2. And to move 1 unit down, the c value must be negative 1. So we can write the transformed equation, g at x equals negative 2 times the square root of 3 times x minus negative 2. Subtracting a negative will make it appear as plus. And then outside of the square root at the end, minus 1. There's the equation of the transformed g of x function. Part B asks us to create a table of values and sketch a graph of the base function and this transformed function. Well, if the base function is f at x equals root x, when I choose my x values, since the function is a square root function, I want to choose x values that I'm able to square root and get integer values. So 0, 1, 4, 9 are a good choice for x values. When I square root each of those values, I get 0, 1, 2, and 3. We could quickly graph what this looks like. There's a rough sketch of f at x. Let's now go back up and apply the proper transformations to be able to get the points for our g of x function. Let's start with what transformations are happening to x, the horizontal transformations. It's being horizontally compressed by a factor of a third, so I could divide all my x's by 3. And then it's shifting 2 to the left. I can move every point 2 to the left by subtracting 2 from all the x's. How we determine those transformations to x is always x divided by k plus the d value. The vertical transformations affect y, and the vertical transformations were a vertical reflection and stretch by a factor of 2, so I need to multiply the y's by -2, and then down 1, so I need to subtract 1. To figure out the transformations to y, we always just do a times y plus c. Now let's do those transformations to each of the points of the base function. The first x value of our base function is 0. When I divide 0 by 3 and then subtract 2, I get -2. 1 divided by 3 minus 2 is about -1.67. I'll use a decimal so it's easier to graph. 4 divided by 3 minus 2 would be about -0.67. And then 9 divided by 3 minus 2, that's just 1. Let's now do the y transformations. Take all of the y values from the parent function and transform them. -2 times 0 minus 1 is -1. -2 times 1 minus 1 is -3. -2 times 2 minus 1 is -5. And -2 times 3 minus 1 is -7. Let's plot all of those points. And there's my transformed g of x function. Question 25, our base function is 1 over x this time. We want to graph g at x, which is a transformed version of f at x. It's f at x plus 1 plus 2. So it's just shifting left 1 and then up 2. We'll create a table of values for the base function and its transformed function. We'll graph the transformed function only and then write the equation of the transformed function. Our base function is 1 over x. The x values I choose for that are usually -2, -1, -0.5. I'll write 0 even though the function will be undefined there. 0.5, 1, and 2. F at x is 1 over x, so just do 1 over each of these values, so just all of their reciprocals. And I get -0.5, -1, -2. 1 divided by 0 is undefined. 1 over 1/2 is 2, 1 over 1 is 1, and 1 over 2 is 0.5. I'll write the rules for how we get the transformations here again. X over k plus d, and ay plus c. In this question, we just have a d and a c value. So for the x, I just have to do x plus d. But remember, d is what we're subtracting from x, so I must be subtracting a -1. So I have to do x plus -1, which would just be x minus 1. My c value is 2, so I do y plus 2. Let's perform all those transformations to the x's and y's from the base function. And now when I graph this transformed function, when it's undefined, I know that's going to show up as a vertical asymptote. So there's going to be a vertical asymptote at x equals -1. For this reciprocal function 1 over x, I know there's also a horizontal asymptote. It's usually on the x-axis at y equals 0, but the c value can shift that horizontal asymptote up or down. Since the function has been shifted up 2, the horizontal asymptote is going to be at y equals 2. A general rule for this transformed 1 over x function, the vertical asymptote is at x equals whatever the d value is, so in this case x equals -1, and the horizontal asymptote is at y equals whatever the c value is, so in this case y equals 2. Let's plot all of the points. Now when you connect the points and draw the function, make sure your function just approaches the asymptotes but never actually crosses or touches them. And this function gets split into 2 branches, and the actual name of the shape of this type of function is called a hyperbola. The last thing I have to do is write the equation of this transformed function. The transformed 1 over x function, its format is going to look like a over kx minus d plus c. So for this question, there is no a or k value, so it's just going to be 1 over x minus -1, which just shows up as x plus 1. And then after the fraction, I add the c value of 2. Section 5, we're on to exponential functions. Exponential functions, there's a few formulas we'll use. Let me scroll to the formula page so you can see them. So on the formula page, notice I have 3 formulas here for exponential functions. A times b to the x is just the general format. If the growth or decay factor is given to us as a rate or a percentage, we'll use the middle formula. And if it's a compound interest question, we'll use the last formula. David bought a new car for $30,000. Its resale value will depreciate by 22% of its current value every year. What will his car be worth in 5 years? So for this one, the formula we're going to use is y equals a times 1 minus r to the power of n. A stands for the initial value, so off to the side, it tells me the initial value is 30,000. R is the rate of decay. So the rate is given to us as a percentage. We need to change that to a decimal. 22% means 22 divided by 100, which is 0.22. And n, the number of times it's going to depreciate by 22% over 5 years, it's going to lose 22% 5 times. If I plug all of this into my formula, I can just use my calculator to evaluate this. And I've figured out that it's worth $8,661.52. So that's my final answer. I'll make sure to communicate that clearly here. 27. The population of a pod of whales has doubled in size recently over a 6-year period. They have a current population of 21 individuals. What might the population be after 15 more years? For this one, I'm just going to use the general formula, y equals a times b to the x. So off to the side, what does the question tell us? The current population is A, that's at 21. B is the growth or decay factor. Since the population of whales is doubling, we're going to set the growth factor to 2. And X is always the number of times it's going to be multiplied by the growth factor. And we can calculate that by doing the total amount of time, in this case it's 15 years, divided by the time of one growth period. Well, it takes 6 years for it to double, so 15 over 6 will tell us how many times it's going to double. If we sub those into the formula, once again, we can use our calculator to evaluate this. It's about 118.8. So our final answer, 118.8 whales. 28. A radioactive isotope decays rapidly with a half-life of 5 minutes. For a 25-minute test, technicians need at least 7 grams of the isotope to be there at the end. How much must they start with? So for this one, our formula is still y equals a times b to the x. But this time, we know the future amount. We know y. We want there to be 7 grams at the end, but we don't know a. We don't know the initial amount. B is my growth or decay factor. For any half-life question, your decay factor is a half, so b is a half. Our initial value repeatedly gets cut in half. But how many times is it going to be cut in half? What's our x value? Remember, x is always equal to the total amount of time, so the test is 25 minutes, divided by the time of one decay period. How long does it take to decay once? Well, it takes 5 minutes to decay once. So x is 25 over 5, which equals 5. So that means it's going to decay 5 times in 25 minutes, and that should make sense because it decays once every 5 minutes. Into our formula, 7 equals a times a half to the 5. To isolate a, we would just divide that power to the other side. So a would equal 7 over a half to the 5. We could probably do this one without a calculator. 1 over 2 to the 5, well, 1 to the 5 is 1, and 2 to the 5 is 32. Dividing by a fraction, we just flip and multiply, so a is just 7 times 32, and 7 times 30 is 210. 7 times 2 is 14. Add those together, 224. So in order for them to be left with 7 grams of the isotope at the end, they must start with 224 grams of it. And then in that 25-minute test, it'll have decayed all the way down to 7 grams. Our last exponential function question: how long does it take $100 to grow to $500 if the amount is invested at a rate of 13.5% per annum, compounded semi-annually? So we'll use our compound interest formula. And what do we know? The principal amount is what we start with, $100. And we know the future amount. We want it to grow all the way up to $500. We know the interest rate per year is 13.5% divided by 100, so we get the decimal of 0.135. N is the number of compounding periods in 1 year. So it's compounded semi-annually, so that's going to be 2 compounding periods a year. And T That's what we're trying to solve for. What is the total number of years they'll need to leave this money in the account so that it grows up to $500? Well, let's sub in everything we know. And then let's figure out how we're going to solve this. Well, let's start by dividing the 100 to the other side. 500 over 100 is 5. And then 1 plus half of 0.135, that would be 1.0675 to the power of 2t. Anytime your unknown is in the exponent, we're wondering what exponent goes on 1.0675 to make it equal to 5. Well, that's what a logarithmic function is for. A logarithmic function can tell us what the exponent equals. It can tell us what 2t will have to equal. We can use a logarithmic function by making the base the same as the base of the power, 1.0675, and then we'll make 5 the argument. What this function is doing, it's asking what exponent goes on 1.0675 to make it equal to 5. And let me show you on the calculator. It's about 24.64, and then to isolate t, we would have to divide that 2 to the other side. So let me just divide that answer by 2, and I get about 12.32. So my final answer, it would take 12.32 years for that $100 to grow to $500. Let's move on to the trigonometry section of the exam. The first part says to draw both special triangles learned in this unit. Let me just quickly draw those. We have the isosceles one, where the angles are 45 and 45, and the side lengths are 1, 1, and root 2. And then we have the half equilateral, which is 60 degrees, 30 degrees, and then side lengths of 2, 1, and root 3. These special triangles can help us get exact values for different trig ratios. And that's exactly what question 31 is asking us to do. Find the exact values of each of the following ratios, show all of our work including a sketch of the terminal arm and its reference angle. So let me start by labeling the angles on the x and y axes. And I'm also going to label cast rule. Now for part A, I want the sine value of 225 degrees, so let me draw the terminal arm. 225 degrees would land me in quadrant number 3, halfway between 180 and 270. If I want the reference angle, that's the acute angle that is between the terminal arm and the closest x-axis. So the angle between 225 and 180 is 45 degrees. That's my reference angle. I can use that reference angle and the cast rule to help me find the exact value of sine 225. Sine of 225 would be equal to sine of its reference angle, but because I am in quadrant 3 where only tan is positive, I know that any sine ratio in that quadrant would have to be negative. So sine of 225 is equal to the negative of sine 45. And if I look back up to my special triangles, sine of 45 degrees, sine means opposite over hypotenuse, so it would be 1 over root 2. So this equals negative 1 over root 2. And then if I rationalize this denominator by multiplying top and bottom by root 2, I get negative root 2 over 2. That's the exact value of sine 225. And as long as your calculator is in degree mode, you could verify that answer. Part B, we want the secant of 300. Let me actually start by changing secant to a primary ratio. Secant is the reciprocal of cosine, so the ratio for secant of 300 would be equal to the reciprocal of the ratio of cosine of 300. So I can say it's equal to 1 over cos of 300. And 300 degrees, that would land me in quadrant 4 between 270 and 360. Its reference angle would be the angle between the terminal arm at 300 degrees and the closest x-axis. So the angle between 360 and 300 is 60 degrees. That's the reference angle. Because I'm in the cosine ratio, I know that in that quadrant all cosine ratios are positive. So I can replace cosine of 300 with cosine of its reference angle, and I can leave that ratio positive because in quadrant 4 cosine is positive. Cosine of 60, if we remember our special triangles, cosine is adjacent over hypotenuse, so 1 over 2. So I have 1 over 2. That means the reciprocal of 1 over 2, so just 2. Secant of 300 is 2. Question 32 wants us to solve some equations. It says solve the following equations for theta between 0 and 360. Round answers to the nearest degree if necessary, and show work. For these questions, let me label the angles again. And I like to start these questions by figuring out what quadrants my answers are going to be in. If we have a ratio between -1 and 1, we're always going to get 2 answers for an angle that has that ratio. So for sine theta equaling 3 over 5, I know I'll get two answers. The ratio is positive, and sine ratios are positive in quadrant 1 and 2. So I know there's going to be an answer, one in quadrant 1, and another answer in quadrant 2. And I know those answers are going to have the exact same reference angle. Usually we use beta to indicate a reference angle. We can use your calculator to get the first answer. Your calculator always gives you the smallest possible answer. And I can get that answer by asking my calculator what the inverse sine ratio of 3 over 5 is. Using the inverse function tells my calculator that I know the ratio and want the angle. And the calculator said 36.8 degrees, so it said round to the nearest degree, so that's about 37 degrees. That's one answer. Sine of 37 is about 3 over 5. If your principal angle is in quadrant 1, that's also equal to the reference angle, so the reference angle is 37 degrees. So to get angle 2, notice to get from the positive x-axis, which we call the initial arm, all the way counterclockwise to the second terminal arm, I could calculate that angle by doing 180 minus whatever beta is. So for this question, I just do 180 minus beta, which is 37. And that gives me 143 degrees. So sine of both of those angles should be about 3 over 5, or 0.6. Part B says secant theta plus 2 equals 0. Well, let me rearrange this equation first to isolate the trig ratio. So secant theta equals negative 2. And then remember, secant is the reciprocal of cosine. So if secant is negative 2, cosine would be the reciprocal of that, negative 1 over 2. I have a negative cosine ratio, so I know my answers are going to be in quadrant 2 and 3 based on cast rule. So I will draw an answer in both of those quadrants. We could use your calculator to get the first answer. The calculator would tell us the angle from positive x all the way over to here. And we could get that by asking the calculator what inverse cos of negative a half is. And the calculator would tell us that it's 120 degrees. And then we could use that information to calculate angle 2. But we actually don't need a calculator for this question, because if you notice a cosine ratio being 1 over 2, we can make that cosine ratio from a special triangle. Cosine of 60 is 1 over 2. So I would just place my reference angle of 60 in the two quadrants that make cosine negative. And now I can calculate the principal angle that has those reference angles. Principal angle 1 isn't a full 180, it's 60 less than that. So angle 1 would equal 180 minus 60, which is 120 degrees. And angle 2, notice it goes past 180 by 60 degrees. So we would do 180 plus 60, and that would give me 240 degrees. So I have two answers. Cosine of both of those should equal negative a half. Question 32 says angle K is located in the third quadrant with a secant of negative 6. Find exact expressions for the other 5 trig ratios for angle K. Let me just draw a diagram quickly. The angle is in the third quadrant, so 1, 2, 3. It's down here. Here's angle K. Let me just draw a right triangle by connecting it to the x-axis. And then it tells me secant of whatever angle K is equal to negative 6. Secant's the reciprocal of cosine, so cosine of K would equal negative 1 over 6. Well, I know cosine of K is negative because we're in a quadrant where only tan is positive, but cosine of its reference angle would just be 1 over 6. So from the reference angle, I'll call it beta. Cosine, which is adjacent, would be 1 over hypotenuse, which is 6. And then if we use Pythagorean theorem to solve for the third side, we would get root 35. Knowing all three sides of this triangle, I should be able to write all of the ratios. When I'm finding all of the trig ratios for angle K, I can use the reference angle to help me find it, as long as I check cast rule to see if I have to make the ratio negative or not. Because I'm in a quadrant where only tan is positive, I know that only tan and cotangent will be positive. The other 4 ratios are going to be negative. So I'm going to put some negative signs by all 4 of those now. Sine of K, I can go to the reference angle and do opposite over hypotenuse, which would give me root 35 over 6. So my answer is negative root 35 over 6. Cosecant is the reciprocal of sine, so I just flip it to become negative 6 over root 35. cosine of k, I can do cosine of the reference angle, as long as I make it negative. So I get negative 1 over 6. Secant's the reciprocal of that, so negative 6 over 1. Tan, I can do tan of the reference angle, and I can leave it positive, because we're in quadrant 3 where tan stays positive. So tan of the reference angle, opposite over adjacent, is root 35 over 1, so tan of k is also root 35 over 1. Cotangent's the reciprocal of that, 1 over root 35. I now have a trig identity to prove. When proving a trig identity, we separate into left side, right side, work on both sides completely separately, and try and prove that they are in fact equivalent functions. And let me scroll to the formula page so you can remember what trig identities we are allowed to use when doing this proof. I've got the reciprocal identities, the quotient identities, and the Pythagorean identities. The first thing I like to do is if I see something that is not a sine or a cos, I like to use an identity to rewrite it as a sine or a cos function. So on the left, I have cos theta over secant theta, but secant I could rewrite as 1 over cosine, minus sine over cotangent. Cotangent, I can use the quotient identity to rewrite that as cosine over sine. On the right side, cotangent, once again, I'll change it to cosine over sine. That's getting multiplied by cos theta, minus tan theta, which I'll rewrite as sine theta over cos theta. And this is all over cosecant, which is the reciprocal of sine. Now when dividing by a fraction, that just means flip and multiply. So cosine divided by 1 over cos is the same as cosine times cos over 1, which is just cosine squared of theta. Minus sine divided by cos over sine is the same as sine times sine over cos, which would just be sine squared theta over cos theta. Let me move to the right before I decide what more I'm going to do with the left side. On the right, in the numerator, I have cos over sine. I forgot my theta there. Cos over sine times cos, that's cos squared over sine, minus sine over cos. That's being divided by 1 over sine, so I'm going to flip and multiply it by sine over 1, which is just sine. And if I were to distribute that sine function to both of the terms in the brackets, you'll see that we actually have it equal to the left side of the equation. The first multiplication, sine theta multiplied by cos squared over sine theta, the sine thetas cancel and we just have cos squared theta. We multiply it by the second term, sine theta times sine over cos, I get sine squared over cosine of theta. Notice that's exactly the same as what's on the left side of the equation. We are done our proof. Left side equals right side. Question 35 just says, determine the equation of both the sine and cosine function that models the function in the graph below. Well, remember a transformed sine function would be y equals, a is outside of the sine function, k and d are part of the argument in brackets, and c goes outside of the brackets. So from this graph, let's figure out a, k, d, and c. A, d, and c are going to be the same when we're writing both a sine and cosine function. The only thing that's going to be different is d, the horizontal shift. Let's start by looking at a, which would be the amplitude of the function. That's half the distance between max and min. We can get that by doing max minus min over 2. So I look at the y value of the maximum, which is 2, minus the y value of the min, which is negative 4. So 2 minus negative 4 over 2, that gives me 3. K determines the horizontal stretch or compression that's happening to the function. We can calculate that by doing 360 divided by the period of the function. Remember, period is the horizontal length of one cycle. If I map off between these maximum values, the horizontal length, that would tell me the period of the function. The distance between 45 and 225 is 180 degrees. So to calculate K, 360 over 180 is 2. That means there's been a horizontal compression of a half that is happening. The C value is like the horizontal midline of the function. It's the line that divides the function in half. To find the middle of something, just average the max and min y values. So add them and divide by 2. So I get 2 plus negative 4 over 2, which is negative 1. And notice if I were to draw a horizontal line at y equals negative 1, that would divide the function exactly in half horizontally. And the last thing is the horizontal shift, the d value. For sine and for cos, we're going to get two different d values. The cosine one is easier. We're just looking what is the x value of a maximum point. So if I look at that point right there, the x value of it is 45. For sine, to see what horizontal shift has happened, we're looking for the x-coordinate of a rising midline. That point right there is where a rising line of sine intersects the midline of sine. The x-coordinate of that point is 0. I can plug those parameters into a transformed sine and cos function, and I'll write them below. Question 36 is our last trigonometry question. It's a Ferris wheel question, so let me quickly draw a Ferris wheel. The question says this Ferris wheel has a radius of 15 meters and is 2 meters above the ground at its lowest point. Let me work that into my diagram. If the radius is 15, I know the diameter is 30. It says the rider enters the car from a platform located 20 degrees around the rim before the car gets to its lowest point. I've worked that into my diagram as well as the fact that it rotates counterclockwise. Part A says graph 2 complete rotations of the rider's height versus the angle of rotation. So my y-axis is the rider's height, it tells me, and my x-axis is the angle of rotation. It may be helpful to notice in the diagram I've drawn, the minimum height the rider is off the ground is 2 meters, and the maximum height when they're at the very top of the wheel, they would be 32 meters off the ground. So I need my y-axis scale to go as high as 32. It's going to take 360 degrees to go all the way around this wheel, and I need to do 2 rotations, so I need 720 degrees along the x-axis. And then using what we know from the question, we should be able to graph 2 rotations. Now, I don't know the height exactly at the start. Once I get the equation in part B, I suppose I could calculate that. But for now, I would know the height once they've rotated 20 degrees. They'll be at the bottom. So at 20 degrees, the height is going to be 2 meters. So 20 degrees at 2 meters, that's approximately right here. When they've rotated 20 degrees plus another 180 degrees, so when they've rotated 200 degrees, they'll be at the very top, which is 32 meters off the ground. So 200 degrees, they'll be at the very top of the ride. And now, because this function is periodic, and I know the period of the function is 360 degrees, from both that max and min point I have plotted, if I move 360 degrees to the right, I would be back at another max or min point. So the first point was at the point 20, 2. So I know it'll be at a height of 2 again, 360 degrees later, so at 380 degrees, it'll be at that height again. And then again at 740 degrees. It's at the max height at 200 degrees, 360 degrees after that, 560 degrees, it'll be at a maximum height again. It might help if I get some points along the midline of the function. And before I do that, actually, let's go ahead and write the equation first. That's going to help you see what the midline is. When I write the equation, remember we're going to want A, K, D, and C. The A value would be max, which is 32, minus min, which is 2, over 2, and we get 15. K is 360 over the period, and for this function, the period is 360, so there's no horizontal stretch or compression that's happened. K is just 1. The C value is max plus min over 2. That'll find us the middle of the function. That's 17. And the D value for cosine, we want the x-coordinate of a max. The x-coordinate of the max was at 200 degrees. And that was because they had to rotate 20 plus another 180 to get up to the max. And for a cosine function, the D value is the x value of a max. So our cosine function, height at a given angle, I'll call it A, equals 15 cos A minus 200 plus 17. Notice I've labeled some of the points. That's just going to help me with what I'm doing next here. The function's going to be at the midline horizontally halfway between the max and min points. So if I go to 110, I can plot a point at the midline. And then the max is at 200, the min's at 380. Halfway between 200 and 380 would be 290. So go to an x value of 290 and I can plot a point on the midline. And then do the same thing between the other max and min points. And then I can connect all of these. And there we go. I've got 2 full rotations of the rider on this Ferris wheel. Let's move on to the last section of this exam, which is sequences and series. 37 says state if it's arithmetic or geometric. Write the formula for the general term, calculate T10, and then calculate the number of terms in the sequence. So for part A, I noticed that to get from one term to the next, you just add 7. There's a common difference between the terms. So for that reason, this is an arithmetic sequence. Part 2, when I write the formula for the general term, I know it's Tn is equal to A, which is the first term, plus n minus 1 times d, which is the common difference, 7. So I could use that formula to calculate term 10 just by subbing in 10 for n, and I get term 10 is equal to 16 plus 9 times 7, so 16 plus 63 is 79. And then part 4 asks us to use that formula to figure out how many terms are in this sequence. The sequence stops at 583. So I'll say 583, the value of the term is 583, equals 16 plus n minus 1 times 7. When I rearrange this to isolate for n, I'll subtract the 16 over, then I'll divide the 7, and then add the 1. So part 4, I figured out there are 82 terms in this sequence. Part B, there's not a common difference between terms, but there's a common ratio, meaning if I multiplied a term by a half, I would get the next term. So for that reason, I know this is a geometric sequence. The formula for the general term of a geometric sequence is Tn equals A, which is negative 36, the first term, times the common ratio, a half, to the power of n minus 1. Let's use that formula to evaluate the 10th term. The value of the 10th term equals negative 36 times a half to the 10 minus 1. So let's use our calculator to evaluate this. It equals negative 9 over 128. And look, that actually tells us the answer to part 4 as well, because notice that is the last term of the sequence. So that tells us part 4, there are 10 terms in this sequence. If you're curious how we could have solved for that algebraically, you can watch me do that quickly here. I'd set the value of the term equal to negative 9 over 128. I'd isolate n by first dividing the negative 36 over, and then I could use log to help me solve for what exponent goes on a half to get 1 over 512. It would tell me the exponent is 9, so I know n minus 1 is 9. Add the 1 over, I get n equals 10. 38. A jogger runs 300 meters in the first minute. The distance the jogger covers decreases by 20 meters in each succeeding minute. What total distance does the jogger run in a 10-minute run? Because there's a common difference between each value in this sequence, I know this is an arithmetic sequence. The formula for adding up all the terms in this sequence, we call that the formula for an arithmetic series, and that formula looks like this. So the sum of the first 10 terms in this series would equal 10 over 2 times 2 times the first term, which was 300, plus 10 minus 1 times the common difference. It goes down by 20 each time, so the difference would be negative 20. And then we can evaluate this. The sum of the first 10 terms is 2100 meters. Question 39 says determine A and D and then write the formula for the nth term of the arithmetic sequence. If we know term 8 is 79, term 21 is 235. Remember the formula for the general term of an arithmetic sequence is Tn equals A plus n minus 1 times D. We need to solve for both A and D. When we need to solve for two variables, we have to make two equations. And because it gives us two terms, that should be no problem. Term 8 is 79. So I can say 79 equals A plus 8 minus 1 times D, or 79 equals A plus 7D. There's my first equation. And then my second term, term 21 is 235, so I can say 235 equals A plus 21 minus 1 times D. 235 equals A plus 20D. There's my second equation. Two equations with the same two variables, we can just use substitution or elimination to solve for them. I'll use elimination. Let me rewrite the equations stacked on top of each other. I can eliminate the a's by subtracting the two equations. So I'll subtract everything. I get 156 equals 13d. And then divide the 13 over. I figure out d is equal to 12. I can sub that back into either of the original equations, so I'll sub it into equation 1, and then get my answer for a. If I isolate a, I figure out a is equal to -5. That means my formula for the general term would equal -5 plus n minus 1 times 12. And then the very last question of this exam, it says use Pascal's triangle to expand this binomial. Remember, Pascal's triangle looks like this, where it starts at row 0 and then goes row 1, row 2, row 3, row 4, and so on. I only wrote the first 4 rows because the exponent on the binomial is 4. I'm only going to need to know row 4. When using Pascal's triangle to expand, if the exponent's 4, I'm going to get 5 terms. Within each term, the coefficients are going to be what I see in row 4. So the coefficients are going to be 1, 4, 6, 4, and 1. And with each of those terms, there's going to be a 2x and a -3y. Now I have to figure out what exponent goes on each of those factors of 2x and what exponent goes on each of the factors of -3y. The exponent on each of the factors of 2x start at a value equal to the exponent on the binomial, which is 4, and then goes down by 1 each time until we get to 0 on our last term. And then on the -3y, it does the opposite. It starts at 0 and goes up by 1 each time until we get equal to the exponent on the binomial, which is 4. This will get me all of the terms in the expansion. I just have to use my exponent rules to simplify this. My first term, I've got 1 times 2x to the 4 times 1. So 2 to the 4 is 16, so I have 16x to the 4. My next term, I can see it's going to be negative. My coefficient is going to be 4 times 2 cubed. 2 cubed is 8, so 4 times 8 is 32. Times a -3 is -96. And there's going to be an x cubed y with that. My next term is going to be positive, I can tell, because of the squared on the negative. To get my coefficient, I'll do 6 times 2 squared times -3 squared, which will give me 216 x squared y squared. My next term I can see is going to be negative. I can get the coefficient by doing 4 times 2 times -3 cubed. That's going to give me -216 xy cubed. And then my last term is 1 times 1 times -3y all to the power of 4. Even exponent, this is going to be positive. -3 to the 4 is 81, so I have 81y to the 4. There we go. It's fully expanded. That's the end of the exam. Hopefully that helped.